All right, everyone, let's get started while we wait for Tom Berger to arrive. So today we have Jenna Samra with us. Jenna is a PhD student at Harvard University in applied physics. And Jen was working on the Eclipse experiment on the NCAR G5 plane. And she's going to tell us about that today. So Jen is visiting HAO for last month and a half, and will be here through November 11th. Jen is a pre-doctoral fellow, at the Smithsonian Astrophysical Observatory, where she contributes to solar instrumentation projects. And obviously, the AirSpec instrument was one of those. Jen, go ahead.
Thank you. I think this is on. Thanks. I'm Jenna Samra, and I'm going to be presenting our Eclipse science results from the AirSpec instrument on behalf of the whole AirSpec team, including PI Ed DeLuca at SAO, and also Phil Judge of HAO, who conceived this whole idea. It's right over there. So before I get into the AirSpec instrument, I'm going to take a step back and talk about 5 unique experiments. A lot of these many of you will be familiar with for the 2017 August 21st eclipse. So HAO actually had a number of experiments up in Wyoming at 8,000 feet at Camp Wyoba. Instruments including narrowband imaging in the infrared, flash spectra in the chromospheric flash spectra, visible polarization, and the NAI, which is the NCAR Airborne Interferometer, which is a little bit misnamed because it wasn't actually airborne. It was supposed to be on the aircraft with us, but it ended up being at Camp Wyoba with the other ground-based instruments. And this is a very high-resolution Fourier transform spectrometer run by Jim Hannigan at ACOM, and he was the PI of that experiment. And then in addition to these 4 experiments, we had AirSpec, which was observing the eclipse about 40 minutes later over Kentucky from an altitude of 47,000 feet on board the NSF Gulfstream 5 aircraft. So the AirSpec experiment was designed to measure 5 magnetically sensitive coronal emission lines, and it did see all 5. I'll give you that spoiler right now. During the 2017 eclipse from the aircraft. And so the unique kind of parts of this experiment were twofold. First of all, it opened a new IR window in the solar corona. So it was the first time for seeing one of the 5 lines, and it was the first time in general for high spectral resolution coronal imaging spectroscopy in the infrared between 1.4 and 4 microns. And in addition to that, as part of designing the instrument, we had to design an image stabilization platform for the Gulfstream 5. And so this platform is actually transferable to other experiments in atmospheric and solar physics. And so the image stabilization system itself also enables new science on the Gulfstream 5. So on the right here, I have a couple of pictures. There's the AirSpec team, and that's a picture of the AirSpec instrument on the Gulfstream 5. And I'll get into more detail about that later. So I'm going to talk briefly about the science goals, just to give you some background. I'll talk about the instrument design and implementation, especially some of the challenges of the implementation. And I'll talk about the eclipse observation, just an overview of the data that we got during the eclipse, as well as kind of what it was like to be on the plane. That was a pretty unique experience. And then I'll go into some details on the results and finally talk about the next steps. And feel free to ask questions during the presentation if you want to wait till the end, whatever you feel. Okay, so our science goals were to identify 5 emission lines in the corona. These are magnetically sensitive lines between 1.4 and 4 microns. And these lines are sort of our best hope, potentially, for future measurements of coronal magnetic field in the infrared, in the far, mid to far infrared, or mid-infrared, really. And so on the right, we have an image from Phil Judge's 1998 paper, which predicts the spectrum of these lines. And you can see they span from silicon 10 at 1.4 microns to silicon 9 at 3.9 microns. And this is a pretty wide spectral range. And we were hoping to sample these with relatively high spectral resolution in order to get a very good sense of their wavelengths. We also wanted to measure intensities throughout the corona, and we wanted to look for time-varying phenomena such as waves in the lines. So we were able to identify all 5 lines, which was really exciting. We did get some information on radial gradients in the corona. Because of our limited sensitivity, we didn't get so much time-dependent information. But we certainly met our success criteria, and we're going to be improving the spectrometer for the next eclipse, hopefully. So here's an overview of the instrument. On the left here, we have a drawing of the instrument. You can split it into 4 main parts. So if you start from the way the light travels, you start with the image stabilization system, which uses this actively controlled mirror here to direct the sun and keep it at the center of the image. So this is an electronically controlled mirror operating at 500 times per second, keeping the line of sight stable. Also part of the image stabilization system are these knobs here that you can see, which are actually stages that allow the whole bench to translate left, right, and fore, aft in the plane. So in the plane, the fore, aft direction is this long axis of the bench here. And this is necessary because in the plane, we're actually looking out of a very small kind of 6 by 9 inch window. And so in addition to having the mirror pointed at the sun, you have to have it pointed at the sun through the window. And so I would consider this part of the image stabilization system. I'll go into more detail on the stabilization system later. It does get its signal from this fiber optic gyroscope, which is pictured right here. So after the light is stabilized by the mirror, it's fed into this telescope, which is just a standard Cassegrain. And the telescope then feeds the rest of the instrument. So that can be split up into 2 different cameras. The telescope focuses light onto a slit jaw, and the slit jaw camera just monitors a white light image of the slit jaw for context of where we're pointed in the corona. The rest of the light goes through the slit into the spectrometer, where it's split up into its wavelengths and is imaged by the IR camera. And I'll have more details on that in the next couple slides. The whole instrument is mounted on this NSF Gulfstream 5. And so this is an NSF plane. It's run by the Research Aviation Facility, the NCAR Research Aviation Facility down in Broomfield, Colorado, which is where we spent many months doing flight tests last year in December, and then this whole summer before the eclipse. And really the support team at RAF, we couldn't have done any of this without them, so a big thank you to them. So I'm gonna show a movie here that was actually taken by a photographer at the Boulder Daily Camera, and it shows the inside of the plane. It shows us the flight team during one of our pre-flights for the test flights, and so hopefully it'll give you a little bit of an idea of what it's like to work inside the plane and what kinds of things we do with the instrument. So I'm just gonna play it on silent and kind of talk over it. Oops, sorry about that. So as I said, this is for one of the test flights. We wouldn't have been this calm during the actual eclipse flight, but we are getting ready for a flight here. You can see the instrument kind of smoking. There's water vapor coming out. That's the liquid nitrogen that we're pouring in to get it cool for the flight. That's our summer student, REU student, Alicia Vera, PI Ed DeLuca, and Chief Engineer, Program Manager Peter Scheimetz behind him, and I'm also back there. This was the flight crew for this particular flight. We always had a crew of 4 people. The window that you just saw up here is the window that we're looking through. And so the light path that I sort of described before, but you can see it again here, it's as follows. Light comes in through the window, it bounces off the mirror, which is just out of range here, and then goes down along the long axis of the spectrometer here. And then into the IR camera, which you can see right over here. So there are 4 operators. The reason that we needed so many operators was, well, there was quite a lot to do during the flight, so I can describe what some of the duties were. So there's one operator sitting at this rack back here. That was usually me, and that person is monitoring the slit jaw camera, so it's just the white light image of the corona telling us where we're pointed. And then there's another seat over to the on the right hand side of the plane there. That person is monitoring the spectra. So they're looking at the infrared camera and they're looking at the IR spectra the quick look data to see if we've acquired the emission lines that we were looking for. There's another person who's sitting up on the floor here, not during takeoff and landing, but for the duration of the flight, who's sitting up on the floor, actually cranking the bench into position, left, right, and also course positioning the mirror, because it only has a limited range over which it can control. That's our fast steering mirror, which does the stabilization. And finally, there's another person. That was usually our mechanical engineer, Vanessa Marquez. And finally, there was another person who's interacting with the pilots, making sure that our flight track is what we think it is, and during the eclipse, making sure that the timing is what we thought it was when we were going to be entering second contact, and so on. Since we're intersecting the eclipse path in a moving target, it's not quite as simple as it is on the ground. And this just kind of gives you an idea of what it's like inside the G5. It's a pretty cramped space, even for being a relatively big plane. And so right now we're cooling the instrument with liquid nitrogen. I mentioned before, that's what all this tubing is. It's snaking out the door of the plane, and I'll get into the need for that in a little bit. But first I'll talk about the image stabilization system, and then kind of onto the rest of the instrument. So the big challenge for the image stabilization was that we could not test it on an eclipse ahead of the eclipse, right? So we needed to design a system that was completely independent of the image. So typically you would close the loop on the target that you're looking at, and you would get a very accurate image stabilization. Well, we didn't have that luxury, unfortunately, because although we could do plenty of tests on the sun or even the moon, we weren't sure whether our closing the loop would work just the same on the eclipse. And so what we did was we came up with a method that was completely independent of the image. It uses this fiber optic gyroscope, which measures the rotation rate of the plane in 3 axes, yaw, pitch, and roll. And it uses the GPS of the plane to give position information that would allow us to compute the ephemeris of the eclipse. And it basically just crunches the numbers, it does the geometry, and then determines how you have to move our electronically controlled mirror here to tip the sun back into the telescope so that it's right along the line of sight. And so this did, a remarkable job compared to having no stabilization. It was not as accurate as having a closed loop stabilization system would be. And in the closed loop system, what you would have here is you have your slit jaw camera, which right now is monitoring the pointing, but not actually doing anything to correct it. So instead of just having an operator in the loop, taking seconds to respond, you would actually have the camera feeding information directly into the closed loop system. And that's something that we're going to implement next time, now that we know what to expect from the eclipse. As it was, we had 60 millisecond exposure times. That was our max exposure time due to other factors, which I'll get into. And for that 60 millisecond exposure time, our pointing was completely adequate. Our jitter remained below the Nyquist limit for 90% of exposure times shown in this one observation, which is about 60 seconds here. So here's the optical design of the spectrometer. So that was just the image stabilization feeding the telescope. And now here's the telescope and spectrometer, which was another big chunk of that block diagram I showed earlier. The challenge with the optical design of the spectrometer was that, as I mentioned, we had emission lines that we're looking for between 1.4 and 4 microns, which is a pretty wide spectral range. And we wanted to sample them with resolution on the order of an angstrom or 2. And so detectors, IR detectors, really any detectors, they just don't have enough pixels to do that if you just try to take the whole range, right? So we had to fold up the light in kind of an interesting way here. And what we ended up doing was we actually had 4 channels on one detector. And so I'll describe the light path here. Light comes in through the telescope. It focuses onto the slit jaw. There's a slit jaw camera out here, which isn't pictured. The light going through the slit is what enters the spectrometer. Gets collimated here. These are all just spherical mirrors. And then dispersed by the grating. And then is aimed onto 2 different focus mirrors. These are 2 of our channels. So the focus mirrors are tipped slightly differently in order to direct light to the top and bottom of the detector. So that gives us 2 channels. And then by using the grating in 2 different orders, we can actually get 2 more channels. And so what we end up with is we have our 5 lines listed here, and 1 or 2 of them is imaged in each channel. So for instance, we have silicon 9 in first order in the 4 micron channel, and the 4 micron channel is down here. At the same time, we have sulfur 11 in second order on the same channel. So this is really 4 microns and 2 microns. This is 3 microns and 1.5. And so the layout of our detector looks like this. We have spectral information across the x-axis here and spatial information across the y-axis. Our slit length is about a solar radius and a half, and our pixel size was about 2.25, turned out to be about 2.25 arc seconds. The implementation of the spectrometer, it was challenging for a few reasons. The optical design that I showed in the previous slide is actually shown here, implemented. So this is a vacuum chamber that was designed by our mechanical engineer, Vanessa Marquez, in conjunction with Universal Cryo. They were the ones who actually built it for us. And you can see that all of our optics from the slit jaw, the collimator, the grating, the focus mirrors, and into the camera are all enclosed in this vacuum chamber. The reason for that is that out at 4 microns, the thermal infrared is incredibly bright, and so everything has to be chilled to below 150 Kelvin. All of the optics that would be in the light path have to be chilled. In order to chill them to that level, we need to have them in vacuum below 10 to the minus 3 torr. And so that's why they're inside the vacuum chamber. For reference, 1 atmosphere is 760 torr. And so in addition to that, the vacuum chamber, of course, the outer walls that are holding in the vacuum are warm, right? And you need to shield those because otherwise they're going to emit right into your detector at 4 microns or 3 microns. And so this inner wall here is just a piece of sheet metal aluminum that all had to be chilled. The way that we chill this is we fill liquid nitrogen through this fill port here. It goes into the chamber and it actually falls and fills below this floor. So you can see the floor has holes tapped into it. Below the floor is a dewar containing the liquid nitrogen, and on top of the floor we attach copper straps, which then attach to each of our optics and then cool them through conduction. And in addition, this is kind of an early picture of the spectrometer, but right now it's been completely blackened to reduce stray reflections. So everything that you see here that's silver, everything that has a view to the camera or a view to the inside of the chamber has been painted black or taped with black tape in order to completely or minimize the stray light as much as possible. In addition, okay, so we also have an IR camera here, right? So the IR camera needs its focal plane to be cooled to reduce dark current. So the camera focal plane is cooled to 59 Kelvin. It also, the snout that interfaces between the camera and the vacuum chamber has the same kind of shielding that we have inside our spectrometer here. And that's for the same reason, to shield thermal radiation from getting onto the focal plane. It turned out that the camera wasn't as low background as we had hoped. And so with the eclipse coming up in a few months, what we decided to do was this patch. We packed dry ice right between the interface of the camera and the spectrometer. And so this was another job that I forgot to mention on board the plane, was filling dry ice up to 5 minutes before the eclipse, which allowed us to get our exposure time about a factor of 2 bigger than it would have been otherwise. That said, we had originally targeted a 1 second exposure time from our Flux budget. That's the number that we came up with. We ended up at 60 milliseconds because the thermal background was just so high that we were filling half of our well at 60 milliseconds, and we didn't want to go any higher than that during the eclipse. So
is this because the camera isn't that cool?
Yeah, it is cool. So we're actually right now trying to figure out what it's because of. So there's 3 sources, right? There's dark current in the camera. It's not, the focal plane was not able to hold the minimum temperature that we really needed, which was closer to 50 or 55 K without oscillating. So we settled for 59. The dark current is a little higher than we needed. The other issues are actual photons coming from radiation, and there's 2 sources. There's potentially radiation inside the chamber, thermal radiation coming from somewhere, right? We're not sure where yet, but any little hot spot could give you enough photons to completely swamp out your coronal signal. More likely, or a bigger contributor, is probably radiation coming from within the camera. There's a window. Right now the camera has its own vacuum to keep it cold, and there's a window on the camera that's holding the vacuum. And so there's a possibility or a probability that there are photons. The camera snout hasn't been adequately cooled, although they have cooled it, and there are photons coming from there, reflecting off the window, and then getting back into the camera somehow. So the issue with the IR camera was that the companies that we found are not used to working at signal levels this low, right? They're used to looking for people or something much hotter than much brighter than the corona at 4 microns, and so they're not even used to working at exposure times of much more than 10 milliseconds in some cases. And it turned out that their best efforts to do the cooling weren't quite enough, and we're going to work with them to make this better for the next time. So the eclipse observation. So we based our operations in Chattanooga, Tennessee for the eclipse. The reason that we didn't just take off out of Broomfield was because we needed to get as high as possible to get above the atmosphere. For that, we needed to carry as little fuel as possible, and for that, we wanted to be an airport that was close to where we were going to observe the eclipse over Kentucky. So starting at very early in the morning on the day of the eclipse, we started filling with liquid nitrogen to get everything to equilibrium, as close to equilibrium as possible. So we filled for something like 7 hours. Took off a couple of hours before the start of the eclipse. So the start of the eclipse was in this location, which is also known as second contact, was at 1822 UTC. We took off, we flew northwest, we entered a holding pattern where we stayed for about an hour and a half while the sun started to eclipse. This was a pretty nerve-wracking time where you're watching the sun get smaller and smaller, but you can't do anything yet because you haven't entered your flight path. So everybody's just had glasses on and they were looking out the window, and then they realized that the breath was fogging the back window. So we said, okay, nobody can look out the front window where our instrument has to look out. So one of the challenges was you couldn't look out the side windows because the eclipse was at 65, it was noon on August 21st, so it was about 65 degrees elevation. So you're not going to see anything unless you're really laying down in your seat out the side windows. So everybody was looking out the nice optical quality windows that were in the top of the fuselage. So we broke our holding pattern about 20 or 30 minutes before the start of the eclipse, and you can see that the flight path here is not quite just right along the eclipse line, and actually quite a bit of planning went into the flight path. There were sort of two competing goals. One was we wanted to be as close to the center line as possible and flying as parallel to the center line as possible to get the longest eclipse, right? So you might think, well, let's just fly along the center line and let it catch up to us, and that's eventually what we did. But we couldn't stay that way for the whole time, the whole path, because we also wanted to be able to get the sun in the window and acquire it into our camera long before, something like 20 minutes before the eclipse started, not right before. And the sun is moving in azimuth so quickly near noon that we actually had to turn the plane because we didn't have enough range on our benches and our stages in order to do that, and then have the same geometry for the eclipse. So here we're turning the plane, we acquire the sun, and then we tried to turn the plane in order to compensate for the sun's rotation, the Earth's rotation. And this, although we thought that this would work, it turned out to be a bit of an issue. We didn't quite have the range, and unfortunately, right before the eclipse observation, we ended up having to move one of our mirrors move our mirror stage and then move it back, which was what we wanted to avoid. It turned out okay. Another thing that we hadn't quite planned for during the lead up to the eclipse observation, this was something that we couldn't really have known how hard it would be. We were trying to set our wavelength range, which we do by tipping the two focus mirrors that I showed you. They're on adjustable stages, and so we adjust them because as the spectrometer cools down, the wavelengths shift, and we want to make sure that we have a range set that will capture all 5 of our emission lines. The way we do that is by looking at the photosphere, and we know the absorption lines in the photosphere and the atmosphere very well, and so we can line up our range using that. We had never done this on a crescent sun, however, that was rapidly shrinking. We had always done it with the full disk of the sun, where it was really easy. On the crescent sun, our pointing wasn't quite good enough to keep it in the image, or keep it on the slit. And so this ended up taking much longer than planned, and it turned out that everybody was only seated and ready to go about 1 or 2 minutes before the eclipse, which was terrifying. This was a terrifying time. So we collected darks right before the eclipse. Everybody sat down. We were ready to go. We had 4 minutes of totality, which was about 1 minute and 20 seconds longer than everybody got on the ground, because we were flying along the path. And during that 4 minutes, we took 4 observations. So here are the observations. This is a composite of our slit jaw images, kind of what it looked like. And our slit positions are shown in red. So we have 3 positions on the west limb, one of them sampling a prominence right here, and one kind of half on and half off the prominence. And then a position on the east limb where there was an active region just rotating on, and so we got some very bright emission there. So here's our movies, our slit jaw movies. This is just what I was looking at on the slit jaw camera. And you can see our 4 observations. We spent the longest amount of time in this observation on the west limb. The issue here was that Ed, who was looking at the IR data, wasn't actually able to see any emission lines because our thermal background was so high, and our pointing was not of a quality where we didn't have to co-align before we averaged. So he's looking at averages that hadn't been co-aligned and didn't see any emission lines, and we were a little concerned, maybe we're not getting anything. And so we moved to the prominence where he saw a very bright hydrogen line, and that kind of put our minds at ease. Then we moved to the east limb, which was much brighter, you'll see in the observations. And then back to the west limb, where we waited for the flash spectrum. So the flash spectrum at third contact we knew would be in this region, and that's why we wanted to end the observation at that position. We weren't sure exactly what time it would be, so we stayed there for about 50 seconds.
Jenna, were these pre-programmed positions, or were you?
No, so we did try to pre-program them, but it turned out to be safer because it was the software was such that you could lose the pointing by just trying to go to a pre-programmed position. And so it turned out to be safer to just kind of use the arrow keys. I also had the arrow keys, which just moved you a set angle. So I haven't shown it here, but there's some time, 5 seconds, where I'm just arrowing across the sun, and it's just moving, and then I go to some new position. But we did decide, so in the sense that we didn't go there exactly, they weren't pre-programmed, we did decide where we wanted to look ahead of time to coordinate with other observatories. So here's the summary of our infrared data. So I've put on this axis each of our observations, 1 through 4, that I just showed you the slit jaw images for. And on this axis, I have the wavelength. So these are each spectra. So these are heavily averaged. For each of the observations, they're averaged completely in time. So the whole 60 seconds, for instance, is averaged for observation 1. And they're also averaged over about the 35 brightest arc seconds in the spatial dimension. And the spectral dimension, of course, is here. So you can see that we see a lot of lines. We see a very bright silicon 10, magnesium 8, and the first ever, we think, detection of iron 9. I'll get into that more later. And those were the coronal lines that we hope to see in this channel. We also see this unknown line, which we haven't yet been able to identify, but it does look like it's in all the coronal data. It's not just a prominence line. In the prominence observations, the 4 and 2, we see neutral hydrogen, which you would expect in a prominence. And I'll talk about that might be useful for us as well, and why that might be. And finally, the other feature that you see in this data is this kind of lumpy background. And this is due to an incomplete dark subtraction. You can see that it's only on the order of a few counts, but our dark backgrounds were so high and were varying during the eclipse, which I'll talk about, that this was sort of the best we could do so far in removing it. And so what this means is that although we have information on the lines, we have good quality information on the lines, we don't have continuum information here. Or it will be harder to extract, at least. So here's the same thing for the other channel. And so you can see we got our remaining 2 coronal lines in this channel, and we got a very bright, this is the bright hydrogen line that we were actually able to see in flight, and another hydrogen line in the prominences. So I'll talk about calibration, and then I'll go into the actual calibrated results that we have so far. So our calibration scheme was as follows. We do a dark subtraction, which I'll talk about more later, a bad pixel replacement, a geometric correction to make sure that the spectral and spatial dimensions of are parallel with the 2 dimensions of the detector. And to do that, we can use the photospheric lines that they're pretty easy to use for that purpose. And then for the other dimension, the spatial dimension, we can use something like dust that's across the slit, which then gives you a continuous kind of dark line in your spectrum. We needed to co-align the frames. This was really important. This is why we didn't see much in the quick look data during the eclipse. And we could only do co-alignment, of course, along the slit. We do a wavelength calibration by looking at the known photospheric and atmospheric absorption lines. And this is an example here of our wavelength cal. The blue is AirSpec data, and the red is a library spectrum, which is made from a library photosphere multiplied by an atmospheric model. And you can see that there are enough strong lines that you can do a very good wavelength cal. We have this data for before and after the eclipse, which will allow us to also assess how much our wavelength drifted. And finally, we do a radiometric calibration, which the idea behind a radiometric cal is to map your signal on your detector from photons per second to something like spectral radiance. And so you multiply to do that, you multiply by the effective area of your instrument, which is the ATON-DO times the spectral dispersion. And then times all of the transmissions and reflectances of all of the optics inside your spectrometer. And I'll go into how we are determining the effective area ongoing in the next slide. So the radiometric calibration, the plot that I showed right here is actually our estimate, a kind of forward model of the radiometric cal, the effective area, which is just our best knowledge of all of the transmissions and reflectances of all the optics, as well as the pixel size and the geometric area and so on. There is a way to calibrate out errors in that by doing kind of an inverse calibration. And so to do that, we can use a known photospheric times Earth's atmosphere spectrum, and look at how that was measured by the AirSpec instrument. Now, when this is measured, it's measured through a solar filter. So this is kind of an ND, approximately neutral density filter to knock down the photons coming from the photosphere. And also an order sorting filter so that we only have one order on the detector at a time. And then it's measured, this whole spectrum is measured by AirSpec. And if you kind of divide these out, you can figure out that what's left is the effective area. So I just like to point out that Jim Hannigan of ACOM was really instrumental in getting us measurements for our filters using his lab spectrometer. And he also provided one of our library spectra by measuring the photosphere with his FTS, the NAI, at 5,000 feet here in Boulder. So basically what you get is something like this. If we skip to here, the black is an AirSpec measured data set. The blue is what you would get if you assumed the effective areas that we had forward modeled from before. And you can see it's a little bit off. And finally, the red you get after fitting the effective areas using the black spectrum as well as the library spectrum. So you get the measured spectrum and the library spectrum, and you can fit a slightly better effective area. So this work is ongoing. We have new measurements that'll make it probably even better now. So there are some challenges to calibration. The biggest one was the dark background. The dark background changes significantly during the eclipse observation. And to illustrate this in a graph, what I've got here is the brightest observation of the brightest emission line. So this is our silicon 10 line, and you can even see a tiny little other line here that doesn't even make it, onto the scale really. And on the same scale, this 0 to 500 scale, this is how much our mean dark was changing over time. So the mean dark is just the mean of all the pixels in our dark frames. the mean was around 10,000 dN. This is a 14-bit detector, so the max is 16,000. And it was increasing at a rate of about 80 counts per minute. And not only was it increasing linearly, it had this sinusoidal trend superimposed on top of the linear trend. And the reason for this, the linear trend, is because we have dry ice, which is sublimating away during the eclipse observation, and we have liquid nitrogen, which is boiling off. And so the temperature of the instrument is increasing rapidly enough that we can see it in the darks. The sinusoidal trend is probably due to the camera chiller that seems to match up. Now, this data is taken after the eclipse. We took darks for about 5 minutes, and it turned out that they were incredibly useful in actually figuring out what to subtract, because we didn't take any darks during the eclipse. We had to subtract a sine wave on top of a linear trend, and in order to figure out the phasing of that, we were able to use this data. The other another challenge, was that we have these interference fringes on the 4-micron channel of the detector. You can see them a little bit, hopefully, in the image here. And to make them more obvious, I've just taken a mean of all the rows of this image. And so you can really easily see them in the spectrum. And you can see that they really obscure the emission lines. So what we've done here is notch filtered them out, and then the emission lines become much more obvious. So these were just some of the issues of working with this instrument and calibrating the data. So finally, onto the data. So here are our coronal emission lines, all 5 plus 1 unknown 1 that we saw during the eclipse. And this is observation 3, where we had the best SNR, but we've computed these fits for all of the observations. So a couple of points to take away here. We have computed full width half maxes here. They are right now, they're really driven by the instrument line shape, and the full width half max of the emission lines themselves should be more on the order, for instance, for silicon 10 should be closer to 2 angstroms or a little less. So most of this 10 angstroms is the instrument, and the instrument full width half max is changing because of the design of the instrument across wavelength. And so that's something that we're still working on calibrating, so that we can actually figure out what the width of the lines themselves are. But we do have, so we've computed wavelengths, full width half max, and then amplitudes, and we do have a greater than 3 sigma detection in all the lines for this observation, which is pretty exciting. And finally, the last thing that we did was we computed the integrated flux in each line. That's weird. Oh, I never plugged it in. Thanks. We computed the integrated flux in each line using the effective areas from a few slides back, and we compared these with the predictions from Phil Judge's 1998 paper. And it turns out that they're within maybe a factor of 5 for the higher temperature lines, and then these lower temperature lines are even closer, which is about what you would expect, considering that his model for the solar atmosphere was just, a model and represented some average. So there are a couple of new detections. So iron 9, we believe, is the first detection of this line at 2.855 microns. And then we have the unidentified line, which is either because of the design of our instrument, we're not sure whether it's at 1.4 microns or 2.8, because we have 2 orders overlapping on the detector. But they allowed us to get all these lines, so it's not too big of a search space compared to just one wavelength. So why are these lines new? Why have they never been observed before? And so there are 2 major reasons for this. One is that this region, if this is a 2.84 line and not a 1.4, this region of the spectrum is completely absorbed from the ground, so you won't see this in any ground-based observations. And so on the right here, I have a measurement from the NAI, that's the FTS, Jim Hannigan's FTS, of the photosphere just before the eclipse. And you can see that here, this 20 count background here is just the noise level, and this is where the lines would show up if we had, if we could see them. But you can see it's completely absorbed. And here you see a little bit of transmission through the atmosphere of the photosphere getting down to the ground. so that's one thing. So if we're going to find these, we have to look in space-based observatories, space-based data sets. The other issue is that the energy of the transition levels, at least for the iron line where we know the transitions, is too high for photoionized plasmas. So unlike most of our lines, which have a transition to the ground state, this has this 2.85 microns is a transition between two very high energy levels, which wouldn't be excited by the temperatures in a photoionized plasma. So we need to look in a collisionally ionized plasma for these. And so we've begun a search for previous detections. So Phil hunted around and determined that, this short wavelength spectrometer on the Infrared Space Observatory, this is a very likely place, if we're going to find a detection, that we would find it here. So this is observed something like 1,200 spectra of various astronomical objects. And we've sort of searched through all of them and have not found a line at 2.845 microns, and the search for the other two wavelengths is still ongoing. And as far as we know, this is a new detection. So finally, the prominence emission lines, we did see 3 hydrogen lines that we've identified, and then as well as 2 lines that are unknown right now. So this is statistics computed the same as they were for the coronal lines. The one point to make, the prominence lines, in addition to any science that we can actually do with them, TBD, are going to be very useful for calibrating the instrument function, because they're so narrow that the whole width that you see here is pretty much instrument. So for instance, this 7 angstrom Paschen line is a very good characterization of the instrument function at 1.874 microns. And then the question is, how does it change across the detector? And well, that's something we have to model and try to measure, and these will be very good spot checks on that. So finally, we did get some information on the radial gradient of the emission. So this is sort of it gives you an idea of what the data looks like in 3D. So we have wavelength across one axis, and then distance from the limb across the other, so spatial information across the other. And for silicon 10, it remained quite bright some distance from the limb. For the other lines, we started losing SNR earlier on, but right now we can't say too much. We need EIS data to really understand the state of the corona at our positions here. But it does look like potentially the lines have some temperature dependence. The radial gradients have some temperature dependence. So the lines are here with their log TEs, and then in advance of getting ICE data, what we have done is compared the lines to AIA. And so here's the silicon line arbitrarily scaled and plotted on top of the AIA EUV lines. And you can see that it's sort of what you would expect. You can see that it does have, it tails off slower than the EUV lines. And you might expect that because it should be radiatively excited as well as collisionally. Especially close to the limb, you can see the difference in slope here versus here. And in the bright east limb observation, you see a slightly different slope. But ICE will give us more information on this. So finally, a couple of things that we noticed, that are going to be really useful for future observations. And so one of these was the effect of the atmosphere. So it was a bit surprising that the atmosphere actually impacts our lines even at 47,000 feet. And there's an absorption band which overlaps the silicon 10 line, and it doesn't affect the line shape. It's too dim for that, but it does affect the baseline. So you can see that the baseline to the left and to the right are different heights, and this isn't something, it's too quick of a change to be explained by the dark subtraction. And if you overplot the atmospheric transmission, it turns out that there's about a 5% change there, which we're pretty sure is what's explaining this. And so at 14 kilometer, this doesn't really matter for us. We'll still be able to get line wavelength, center wavelengths and full width half maxes and everything. But at 3 kilometers, this might have some implications for ground-based observatories. And in particular, It might mean that atmospheric monitoring in parallel with the coronal monitoring is required for the precision needed for spectral polarimetric observations. And of course, we did have instruments on the ground measuring the same eclipse. And so here's data from the NAI at 8,000 feet, 2.4 kilometers. And you can see that this is shortly before totality started, but you do see an atmospheric absorption or an atmospheric transmission band right here, and it's right on top of where the silicon 10 line should be. There was no silicon 10 line observed. In fact, this is photospheric data anyway. But this transmission band is about as wide as silicon 10. So what are you going to be able to say about, if you did see a line on top of there? Are you going to be able to distinguish? Well, that's sort of unknown. And this, again, is Jim's data from the NAI. So that's the data that we had. And for the next eclipse, we have a couple of improvements that we want to make. The major ones are the three that are listed here. So we need to close the loop on the image stabilization. I mentioned this before. And we need to do that so that we can allow longer exposures. So on the left, I have one of our slit job videos here. And on the right, this is actually a video, although it's hard to tell. This is a video of what we predict our closed loop stabilization can do. And basically, this is just, we figured out how much the image was moving in each frame of this one by fitting the limb. This is work that our summer student, Alicia Vera, is working on right now, actually. And assuming that, if we can measure the displacement, we can correct for it. We then corrected for it in the second video, and you can see that we do a much better job stabilizing. In order to allow 1 second exposures, we can't just stabilize the image better. We also need to really reduce the thermal background. This is what's driving that. And so we're going for a 10 to 15 times reduction in thermal background to allow 0.5 to 1 second exposures, which is going to get us back up to what we predicted originally we would need from our flux budget. Now, I mentioned this a little bit, but the process of doing this is basically you have to attack it from 3 different ways. You have to reduce the dark current inside the camera, which means reducing the focal plane temperature, which means working with the camera company to remove the oscillations that appear, the instability when the temperature controller tries to control at too low of a temp. In addition to that, so that's 1. You also need 2, you need to reduce the thermal background inside the camera. And 3, you need to reduce any thermal background hotspots inside the spectrometer. And so those are things that we're attacking right now. And finally, we need to refine our pre-eclipse operations. Now that we have an idea of what it's going to be like going into a total eclipse, the next one, we won't be caught, fiddling with knobs 5 minutes before totality. Yeah.
Isn't there a square root in these with noise?
Oh, there is. Why did that go away? Yes, there is. But I think what happened was, if you assume, I convinced myself of this. So for a given, if you reduce the thermal background by that much and then don't average, you get the square root. But then by averaging, you get another square root. So this is assuming we averaged as much as we did, right? But then had that much lower background.
But your total amount of observing time doesn't increase.
That's true.
You've only got so much eclipse. So
That's true. Maybe I needed to. Yeah, that's possible that there's a square root in there. Yeah. Okay, I can look at that again. Right, because we would have fewer observations of longer. So yeah, okay. So we have a few follow-on experiments planned based on the results of this eclipse. There's a reflight, hopefully, that we're proposing for in July 2019. Well, we're definitely proposing. We'll hopefully get funded. This one we hope to have an FTS on board, not necessarily the NAI, but maybe a more compact version, which will be really useful for getting high-resolution kind of total sun measurements of the corona. We're following that successful experiment, we'd like to fly a spectropolarimeter, which will actually measure magnetic fields. Right now, we can't measure magnetic fields with what we have because we don't have polarimetry. And so we would choose 1 or 2 lines from our current design and target a future eclipse, maybe December 2020. And finally, a laboratory study of infrared coronal lines using the SAO EBIT might be really useful for determining some of these unknown lines. And that's it. And these are hopefully I didn't miss anybody, I'm sure I did, but many of the people who helped.
We have some time for more questions. Oh, come on, somebody. All right, I'll bite. Oh, Michael?
I want to suggest to name this unknown line coordinate.
Okay.
Following the story.
All right.
Ricky?
Yeah, the unknown line is really interesting. I don't know very much about the history of development of spectral atlases, but you know, my naive assumption is we know all the places electrons can go and all the elements. How can we be surprised?
Yeah, you know, that's a good question. And the last day or so, I've been sort of poring over level lists looking for something that's close. I guess Phil might be able to answer this better, but do we know all of the level transitions? I know we can compute them all, but it seems like there are constantly papers being published saying, oh, here's all the levels of manganese 12, you know, from between X and Y. And so if you look in the NIST database and you see like a whole bunch of missing, transitions or missing levels for a particular element or a particular ion, and then somebody's publishing on this, I don't know. I would argue that there might be something new to learn still. What do you think, Phil? Yeah?
Yeah, I mean, the NIST levels are not complete. There is no complete set of lines the spectra of atoms and atomic ions. I mean, you can quantum number you like, but the ones that are likely to get excited. I was struck by a couple of things. One was that you looked for and found 5 lines. You didn't find 25. You found 6 actually.
Yeah.
So that tells me that in terms of the sun's corona, whatever's forming the lines in that plasma was fairly complete by the NIST levels and parameters that we have for atomic species. But I didn't include transitions with abundances below about I think it was 6 in low abundance compared with hydrogen. So there are things like nickel and manganese and cobalt and stuff that could have something in there. But what's interesting to me is there's nothing in the ISO spectra either, but those are lower resolution. But the puzzle is what that could do.
Yeah.
But you can see how strong this line is compared to other lines that you have observed and that you know what they are, like the iron line, right? So you should be able to kind of estimate a transition probability times a population density or something like that for this unknown line, right? So that should give you some idea of what element it might be.
Yeah, you can do something equivalent to that. I don't know. Anybody have any ideas what to find this thing? I think you can find it with an EBIT.
Oh yeah, I mean that would be one of the main uses of the EBIT if we get that funding.
So an EBIT is this thing where you trap ions. Xi'an Li is not Fudan University in China. They spent a lot of time and the ions live trapped in this little magnetic field for a long time, and when you put this field as many as you need to measure surface scattering properties, which is a laser. The fact you can hold it there for a long time is perfect for these very long-lived states. So you can actually shoot lasers at it and see if you can get these things to respond and find something.
We should have some idea of what to put in, right? I mean, it would be kind of a hunt to go through every. But yeah.
Axel.
So your
The perimeter is flying 2020 at the earliest, right? You're saying.
2019, there's an eclipse over Chile. Yeah.
So my question is.
Oh, the polarimeter. Sorry, 2020. Yes.
2020. And then, are you still planning to measure along 4 different strips next time, or would you have the possibility to cover a broader range of the circumference of the sun?
Oh, I see. You mean the 4 slit positions? No, I think it's completely open. This will be a redesign of the instrument. It's not going to be in 2019. We'll fly the existing instrument, but this one could certainly have a longer slit width, and we could make whatever observation plan we think would give us the best data. So yeah, if there are requirements, I think it would be useful probably for us to talk to HAO people because you guys have so much experience, right. Yeah, with the polarimetry.
Anyone else?
Well, I think for first flight, it's a tremendously successful experiment. Really want to congratulate you.
Thank you. Yeah, I think everybody on the team was really excited. After a few days, when we realized what we had, right away we were just exhausted.
I'll second the congratulations and add that when I did a little bit of research on the history of the last Great American Eclipse, like 1857, where
really?
Langley and Edison were scrambling to get funds, and there's stories like the guy ended up watching the eclipse on his back on Pikes Peak because he didn't have you got altitude sickness.
Oh, wow.
Stories about how you sort of scrambled to put the thing together and managed to get it, I think, fit right in with that.
Yeah, I guess it's just an eclipse thing. You have 4 minutes or 2 minutes, and that's what happens. Yeah, yeah, that's funny.
I have a question. Have you thought about the difficulties you've had with thermal infrared? What things would you give a warning to people who do just about?
Yeah, and that's not a coronagraph, right? I mean, it's
Yeah, it is.
It is, but it. Okay, so there's an occulting disk. Well, the big issue that we had with the thermal infrared was that we were looking all the way out to 4 microns. So if you look, go all the way back to that spectrum, and the DKIS lines are starred here. So if you can choose a detector that cuts off very, beyond or very, very short of 4 microns, and you kind of sample less of the less thermal infrared you can sample, the better, I guess is what I would say. So if there's a line that works that's not the 4 micron line, then it might be worth going to that one, even if you get a bigger lambda squared from the 4 micron. But the big issue for us was the going all the way out to 4 microns and then having a detector that was sensitive all the way out to 5, where you just have so much thermal radiation. So as much as you can reduce those kind of stray things with filters, cold filters, we found that to be really helpful. For instance, just throwing away light that we weren't going to find anything in, or that what you might find isn't worth the background that you get.
But the fact you found a line that wasn't expected should be an incentive to look further out.
Do you think to look further into the IR? Because the line that we found was between 2 known wavelengths.
There might be more stuff. There might be more discovery space.
Yeah, that's certainly possible. I think it's a question of the discovery space, but then I guess if it's not going to be useful because it's so hard to work out there, and you can satisfy your goal of measuring a vector magnetic field or something with a line that's easier to work with and bright enough to offset the benefit that you get. I don't know, maybe. But then again, if you don't know what's out there, how do you know? So yeah, there's an argument for that.
Once you found something, it's easier to refine along. So anyway, I wouldn't dismiss it.
Okay, yeah. No, that's true. It's always easier to refine. That's what we're doing now, and it turns out to be easier.
All right. If there's nobody else, then let's thank Jenna again.
Thank you.